Hello everyone. Today we're going to be talking about VBO, also known as Ball Bar Optimization. This is presented by Mikhail Shah, Jesse Harkness, and David Melendres. This is an overview of what we're going to be covering today. First, we're going to start with what is Ball Bar Optimization, background, history, and some of the benefits of it. Then we're going to be moving to traditional VBO method, such as passive distribution system and the components as well. Then we're going to be talking about power electronics, such as the thyristor, smart inverter, the static bar compensator, and static synchronous compensator. Let's go over the first point here. What is ball bar optimization, BBO? BBO is the process of managing reactive power and voltage level in a power distribution system. This is accomplished using ball bar control devices with the purpose of minimizing losses and energy savings. As we can see here in this graph, we have three different voltage levels. One, when the voltage is too low, so the inverter needs to inject reactive power to satisfy the voltage level required. Then we have a steady voltage level where there's no need for reactive power to be supplied or absorbed. And we have a third level where the voltage is too high, so the inverter needs to absorb reactive power to satisfy that voltage level. Now we will be looking at background of PBO. In the early 2000s, global warming became an important subject, making consumers more aware of the carbon footprint, creating a higher demand for clean energy. Consumers started to get involved, and to offset these carbon footprints, many people started to install solar panels in their houses. The distributed generation created voltage instability, which BBO can fix. As years went by and BBO gained popularity, becoming an important topic to study in power engineering, such an important topic that in 2011, the Smart Grid Demonstration Project selected BBO as one of the four topics for the 2011 strategic research. Let's talk about the history of BBO. Back in 1973, the oil embargo crisis forced utilities to increase efficiency of the power distribution system by reducing peak demand to conserve energy. During this time, utilities such as Pacific Gas and Electric and Southern California Edison Company began to test the concept of lowering the voltage to lower the energy consumption of the power delivery system. Due to positive results, the California Public Utility Commission required to the state utilities to lower their range voltage from 114 to 126 to the new one, which is 114 to 120 volts. As the energy crisis stopped being an issue for energy generation in the 80s, utilities stopped using the concept of lowering the voltage less and less. Then in the early 2000s, emission control and global warming became a hot topic, and utilities once again started to focus on conserve energy and also avoid emissions. With more than 20 years of technology improvements, the focus of minimizing energy consumption shifts to controlling not only voltage but also bar levels in near real time with ball bar optimization methods. Let's go over some of the benefits of PVO. Satisfy voltage requirements. As mentioned before, bars can be supplied or absorbed to manipulate voltage levels to satisfy these voltage levels requirements. Reduce emission. Ever since energy consumption is lower, the fuel use and the greenhouse gas emission is reduced as well. The transmission efficiency is improved mainly by reducing losses, and the performance of the distribution system is improved with better energy efficiency and energy conservation.
Point number 2, traditional VVO. Traditional volt-bar optimization was designed around a passive distribution system. This meant that power generation was done centrally and distributed out to substations and radial feeders. This meant that power flow is typically just in one direction. Now, VVO consists of the following components: on-load tap-changing transformer, line regulators, and switch shunt capacitors. On-load tap-changing transformers are typically found at power substations. These are special kinds of autotransformers that allow for turns ratio adjustments with their tap settings while the system is under load. This is important so that power isn't disrupted to customers while changes need to be made. The way that these transformers are used in VVO systems is that they allow the voltage to be increased as load is added to the feeder lines over time. The next component of traditional VVO are line regulators. These are typically installed along feeder lines and are used to boost up voltage as it drops from residential loads along the way. Like on-load tap-changing transformers, these are also auto transformers. But inside, they're a little bit different. There's two magnetically coupled coils. The first coil is fixed, and the second rotates, and this rotation is what causes the voltage to change. They could be either manually adjusted or automatically with a servo control mechanism. On the right, you'll see the schematic of the line regulator. As you can see, there are two inductors inside this regulator that are magnetically coupled. The first one is fixed. The second one rotates. Depending on the rotation of the second coil will determine the total voltage output. For maximum voltage output, 0 degrees rotation would produce around double the voltage. And to have the minimum input, rotating all the way around 180 degrees would cancel out the voltage of Vn and generate 0 volts. This is useful so that the line regulator can custom tailor the voltage output as it needs to boost the voltage on the feeder lines up to the per unit value. The last component of the traditional volt-VAR optimization being discussed today is the switch shunt capacitor. As can be seen with the power triangle on the right, as the inductive reactance increases, and so do the VARs, due to motors and other devices on the feeder lines, the switch shunt capacitors are added to offset this and in turn bring the power factor back down closer to unity. This restores voltage down the feeders and reduces the current drawn by the loads. The flow of VARs is proportional to the magnitude of voltage differences on the lines. This is why it's important that the voltage is maintained within PU range all the way down the feeder. The switch shunt capacitor is important in that it can be turned off and on as the VVO program requires.
We will now look at power electronics in VVO. Our first item will be thyristors, and we will see how they work. Then we'll move on to smart inverter and see how they can generate reactive power. Then we will look at static VAR compensator or SVC and static synchronous compensator or STATCOM, and we will see how they work and see how they are different. Thyristors, also referred as silicon control rectifier of SCR. And here on the left, we have a diagram of the thyristors. We have an anode on top and then a cathode at the bottom, and then we have a gate that controls it. A thyristor is composed of 4 layers, usually PN, and when we apply a higher voltage here at the anode and a lower voltage here at the cathode, we are forward biasing this PN junction here and also this PN junction here. This means that the voltage at this junction is higher here and smaller here, higher here, and smaller here. This junction over here is still reverse biased because since we're applying a high voltage on top, then that means, a lower voltage at the top, that means the bottom must be a higher voltage, and here that means we have a lower voltage. When we apply a voltage through the gates, we are raising the voltage of that P section, which means we now have a higher voltage and a lower voltage here, allowing the current to flow through. Consequently, the current can flow through the entire thyristors. The advantage of using a thyristors is that we don't have to apply constant voltage to control the thyristors. All we need is just a pulse, and this can be better seen on the VI curve on the right. The voltage can be built up throughout the thyristors until we actually trigger the gate, and the voltage will drop down. The current will be allowed to flow through as long as there is current. Once the currents drop back down, and then we are reaching the limits of the latching current, the thyristor will close down and will need to be re-triggered at that specific voltage to reconduct the current. We will now look at smart inverters. They are usually connected to a solar panel, and their primary function is to convert DC to AC because the output of the solar panel is DC, but then our houses and the grid are AC. The smart inverter has the capability to synchronize automatically to the grid. That means it can match the voltage, amplitude, frequency, and phase angle. And the additional features that the smart inverter has is that it can generate or absorb VARs. The question is, how can we generate VARs out of a DC system regardless of the load? If we consider the circuit on the left, we can model the system. We can assume that the voltage is already converted into an AC wave. That's why we have an AC generator. And since we don't want the load to generate or absorb any VARs, then we can assume that it's purely resistive. If you use a switch and open it and close it whenever you need it, then you can absorb or generate VARs. If you look at the graph on the right, it's easier to understand why. The blue curve represents the voltage, and so we can expect the current to follow a same pattern. However, if we open and close the switch, we can get the dash curve here. The yellow curve represents the effective current that we're seeing out of that dash curve. And you can notice that we end up having a phase shift between the voltage and the current. If you remember, the angle between the voltage and the current is named theta. And since theta is no longer zero, then Q is no longer zero as well. Static VAR compensator, or SVC, are part of the flexible AC transmission system of FACS device family. There are no moving parts except for the switches inside. It aims to control the power factor by using capacitors or reactors. It has a very fast response because the capacitors and reactors are controlled by thyristors. It is not directly connected to the grid. It uses a step-down transformer to downsize the components. However, they still need to be big enough to handle the current. SVCs can be modeled with these circuits. On top, we have the step-down transformer, and on the left and right, we have reactors and capacitors. Those two here are mechanically switched, so that means there is no control over how much reactive power we want to inject or absorb. Those two here are reactors and capacitors controlled with thyristors. In this case, the thyristors allow us to control how much reactive power we want to inject or absorb. Static synchronous compensator, or STATCOM, also belong to the FACS family. They use DC capacitors to generate reactive power, and they have a much faster response than SVCs. They are connected in parallel to the grid, and are usually installed at the substation. Inside the STATCOM, capacitors are connected to BJTs in an H-bridge configuration. This allows us to control which direction the current flow, and so whether we're generating or absorbing reactive power. For example, if capacitor 1 is charged up this way, and we're opening up this switch and this switch. In this case, we'll be generating reactive power because the current will be flowing this way, and it will be fed to the grid. For these capacitors, if it's still charged up this way, and this time we're opening up this switch and this switch. In this case, we're actually absorbing reactive power because the grid will be feeding its current to the capacitors. To conclude, VVO has greatly improved over the past 20 years. It is a process to fix voltage instabilities and improve the overall performance of the grid. We saw that traditional devices involved in VVO have limited and slow performance, but more recent technologies in power electronics provide a much faster response and give more control. However, this also means that we now have more complex systems. Thank you for watching, and good luck on the final.